So today we are talking about project number 2 from this image processing course. We already introduced the data, but I'm going to do that again briefly, and I will be focusing a lot on task number 4, at least to begin with. I have already run the code that downloads the data and so on. So here, if I click on the representation of the hard drive from the Colab computer, I can see all the folders with all the files, just like we did last time. As opening them here is a little bit unwieldy and inconvenient, I will open them in my computer. Before I do that, by the way, you can also download the files to your computer if that's helpful. You can even run the Colab notebooks in your computer if you use something like Anaconda, some data science suite. I think Anaconda is the one that I would recommend. That there are other softwares to run Jupyter notebooks and Colab notebooks. Okay, for this second project, it might be advisable to do so because the needs of the computer, the requirements from the computer to run this project 2 are not too high. For project number 3, if you have a computer with a GPU, you can also do the same. If you don't have a computer with a GPU, do not want to spend time learning about this Anaconda thing and so on, you can still use regular Colab and you can do the projects there, no problem. If you have a fast computer running some of the codes here and some of the codes in project number 3 might be a little bit faster, but if not, everything is absolutely doable from Colab. Just another quick note before I go to see the data again is that I fixed the problem that we had last time. So now we have this new cell there and we can see what I was telling you about last time, this representation of the different folders and the files that are in each one in this text, but tree type of shape. I think that's informative. And if you're so inclined, there is this class here. It's a neat class, not very big, with this make tree method, okay, and use of decorators in Python. So beginners, do not worry about this at all. More advanced users, I think you can give that one a look because it's nice to see and it's a neat solution to this problem of what files do I have, how do I represent them? Well, here you have a nice way to see them in a tree. I've already also run these functions to read the mosaic and read binary images. I have not solved task 1, 2, and 3. I hope you can do those on your own from what we told last time. And now we are going to be focusing on task number 4. But before we do that, let's check again the shape of the data. We have, as we said, now this is annoying. Let's get it somewhere else. We have in our folder several data. Sarah, who, as I said last week, is a former PhD student of the Smart Forestry Lab in the Faculty of Agriculture and who happened to be here last week. We have several folders, one folder for each site, and if we click one of them, then we can see all of these files. We already saw the mosaic file, which is the one that's called s something, snumber.jpg, and then we have others. Today we will not concern ourselves with the boxes one. That's for something else, and maybe I get to tell you guys a little bit about that next week if we have time. But today we are going to be using the ROI, all of the species masks, which are always called the same site something, and then another S, second S, and the code for the species, 04, 05, 08. Not all of the species need be in all sites. Actually, they are not. And so on and so forth until species, I think the bigger one is 44, but you can check that, okay? Finally, I also have one file called treetops. Let's quickly see all of those. So we have the mosaic, in this case for site 4, which is the one that I happened to open before. Nice view, what's that here? Some construction materials here. Okay, this is from a section of the forest in Ensuring. We can see the path. And as we saw last time, we can see the trees with a high level of detail. And that's the strength of drone image processing. You can image still pretty big areas, not as big as satellite imaging, of course, but the spatial resolution that you get is much, much higher. This data is actually not great as drone image data goes. This is, let's say, initial data from when we started working. We means the smart forestry guys and me started collecting images with drones. So now they get much better, much crisper imaging with the same resolution. But still, we get to see the texture of the leaves. We get to clearly identify individual trees. And now we can also do that with fewer image artifacts. Okay. Again, some nice looking trees with some slightly weird image artifacts because of the photogrammetric reconstruction. Remember, the drone flies over the forest with the camera pointing downwards, the nadir position, and all of those images that are taken are superimposed using this photogrammetry technique where coincident interest points in the different images are identified automatically, and then the images are registered to make this mosaic, this collection of pictures with overlapping parts that get you a final image of a larger area, this mosaic, with very high resolution. Okay. And as we said before, first of all, we have the ROI. Sorry, not that one, this one. Okay, the ROI is just a binary mask. And because we're using grayscale images, that means that we have pixels that are basically 255, 255, and pixels, the ones that indicate the correct part, the part that we are interested in, that have value 0. Okay, that correct part means, as we briefly saw last time, that because we have artifacts and annoying parts in the borders, we select the part that's interesting in the middle. Let me give it a little transparency for a second. Okay, not that one, that one. Okay, and then that means that this now highlighted part, we are not interested in the construction material, although we apparently are interested in this machine here. Sometimes that happens. And probably it's close to interesting trees. We identify this part as the interesting part. Let me get rid of the transparency to be able to look at this again. If I get closer, sorry, have black pixels and white pixels, and the black pixels are the interesting ones. I wonder if I can see. These are the pointer values. No, I'm not going to be able to see it. What I wanted to show you, but I cannot see it at this moment, is that things are not always perfectly binary. Okay, if you look at this part here, you will see that now all the RGB values are 255. And if I go here, they all change to 0. Okay, so that's what we expect to achieve. 0 means good information, 255 means wrong information, outside, not interested. Sometimes because of the way the tools that we use to build this mask work, we have values that are neither 255 nor 0. We have gray values in between. Okay, that doesn't, I don't find it here, but it happens in some of the other masks. That's, let's say, artifacts, minor problems with the constructions of the mask. This is, keep it in mind, it's going to be interesting later. Most of the times, the values are either 255 or 0, okay? Why am I seeing them tripled here? 3 times 255 and 3 times 0, because the software that I'm using to visualize this, GIMP, is thinking that these are color images. So it's choosing to interpret the values that I have, I only actually have one, as color images. So it's just copying the value that I have in each pixel 3 times. Okay. When I read this with the readBM function in my notebook, I will only have one value for each pixel, 255 or 10. Okay, I also have, as we saw last time, the species masks, okay, which show me where the trees from one particular species are. One species, another species, third species. These are, again, binary masks. And let me see if I can see some gray here somewhere. Maybe it's not on all of, no, I cannot here either. On some of the masks, maybe here. Let's see. Yeah, here, okay? So this is 255, and this guy is still 255, but I'm getting it visualized as something gray. 229, for example, okay? And this is 225, not 255. So, for example, here, because of the way the masks are constructed, I have some gray. Very whitish looking gray, but gray nevertheless, okay? And here, again, on the other side, I have more, okay? So whenever I check these values, this is 254, which is very annoying, okay? I'm going to have to consider that not everything is perfectly black or not everything is perfectly white. So we saw the ROI that marks where the interesting part of my mosaic is. We are seeing now species masks, and I have one for every site and every species present on the site. And finally, we also have the treetop masks. Okay, all of the trees from the different species all mixed together in this treetops ROI file that, as I have already helpfully given it transparency, shows me the place where the trees are in my image. Okay, so I can see them here, and that is what we mostly already saw last week, but I think we need a bit of a refresher because now we are going to be using that extensively. To sum up, the mosaic, the ROI that shows me where the interesting part is. Okay, not so far. The species masks showing me where the trees from each species are. These are also binary masks. And the treetops mask, where I see where the tops are. Notice that here I have a mask with many connected components. It's a word that we are going to be using extensively in a second. Well, not in a second, in a while, okay? Okay, so that's it. And now would be a good moment for questions in case anyone has some doubt about how the information is organized. It would be a good moment because I'm going to start using it a lot in a second. Any questions at this moment? No? Okay. So, okay. So let's continue. In task number 4, I want to create a label image. First of all, what is even a label image? A label image is a single image that gathers, joins together, encapsulates all of the information about the 3 species. So I have all of the information about the 3 species here, but I have several different files, which is annoying in terms of checking them. Also, I have many possible species, but they are not always on the same not all the species are on every site, which again, annoying. If I want to check something about the tree species, I'm going to be having to check whether every file exists at every moment. So I don't want to do that. I want to organize my information in a way that's a little bit more convenient. Label images, by the way, are very often used in many image processing problems. Okay, not only this drone image processing, but I'm working recently with a colleague that has come for a couple of months visit in medical imaging, and we are using label images there too. It's used for semantic segmentation, which is the most frequent problem where this type of label images are used. In semantic segmentation, we will try to assign one of the possible categories, in this case, either one number of a tree species or the zero value, which accounts for the background, to every pixel in the image, in each of our images. Okay, so we're going to try to separate the different meaning, the different semantic meanings in terms of our problem inside of our image pixel by pixel. This is also very often used, for example, in self-driving cars. A car, Tesla, Waymo, Baidu, is driving, it's taking lots of information, and in each of the image of different types, RGB LiDAR that it takes, it tries to understand. It tries to understand is not a good word for a computer or for an AI, but it tries to assign some semantic value, some value that has an importance in terms of a problem that's being dealt with. In self-driving cars, it will try to identify where other cars are and mark all of the pixels belonging to other cars, pedestrians, the street, the sky, buildings. Okay. This is semantic segmentation, and this is a problem where label images like the one that we are going to build now are used the most. But they are also used, for example, for object detection, because object detection, where instead of assigning values to all of the pixels, I just want to find some things in my image. For example, I could want to find where the trees of one particular species are, and I would mark them with bounding boxes and perhaps also segment, also say inside of the box, this is the part that belongs to the tree and this is just a shadow, okay? In that case, I would also be using label images like we are doing at this moment in one of these forestry image processing, well, not one, many of the forestry image processing in our lab and in the collaboration with the Faculty of Agriculture. At the same time, these object detection networks, we are also using them for, let me show you, kanji processing. Sorry, not kanji processing, WASM document processing and identification of kanji. Haven't been able to finish this, but I hope so. These type of images that I'm going to show you just down here, we also use the same techniques, the same label images, the same types of deep learning networks that we will see in project number 3 to process this type of data. So if you are hearing about these things and not too interested in the particular practical applications, do not worry. These things are general, and that's what makes them so popular. Okay, enough with the ad for label images and deep learning in general. We want to build that label image. We want to, in order to be able to use this information competently for our own processing here in terms of computer vision and for deeper processing later in project number 3, we want to build a label image. We want to gather all of those masks into one single image where every pixel contains a code. That code will be 0 if there is no tree species there, and then there will be the code of the tree species if for every pixel if there is a tree species there. Okay, what does that mean again? Well, for example, here I have site 4 species 12. So for site 4, I will build one label image, and all of these guys, all of these pixels that are black here, meaning that they do contain trees of species 12, these are going to have the 12 code on them. Okay. Then if I open this one, here I have site 4 species 4. These guys and these guys and all of these guys and all of these guys and all of these guys are going to have the code 4 in the label image. That is what I want to achieve. So the proper code for the proper species in the pertinent pixels, and this part is the path and this part is the path. So that should be a 0 because there is no tree species there. So background or things that happen, outside of the ROI, okay, should all be 0. Tree species inside of the ROI should be the proper code 6, 9, 12, 4, or any other code belonging to the tree species, and everything else should be a 0. Right, let's go do just that. I have given you before quite a lot of material. I'm adjusting. I'm a little bit self-conscious because I think this may be a little bit too easy for some of the more advanced students, but hopefully you can have a little bit more fun with the final tasks. And for beginners, I hope that introduces you in a way that allows you to jump right into it. So this first function uses regular expressions, and again, do have a look into them if you are interested, but if you're a beginner, you do not need to worry yourself too much about them. Regular expressions are a very powerful feature of Python. Python has many cool programming things built into it, and this is one of them, but I'm not stopping at them. The point is that this isSpecies mask receives the name of a file and returns true if that name of the file belongs to a tree species mask. Okay, so basically, if I give it the name s4 treetoproy.png, it will say false. Okay, so no. If I give it s4 s12.jpg, it will say yes. So this is a simple function to identify what files inside of each of my site folders are actually species masks. Okay, and that's helpfully named isSpecies mask. Then I have the build GT function, which is the one that you want to implement. Have to implement for task number 4 here. Okay. You will receive the name of one of the folders because, as we saw before, we have actually quite a lot of those. We have 13 different folders. Okay, so you will receive one of these names as something, S7, S8, S11, whatever. And you need to build the label image corresponding to all of the species masks in that folder. Okay, have given you some things quite already done. For example, let's start running some things. Well, no, we don't need to. Yeah, let's try to print this one. This might be helpful in terms of debugging and using the code and so on. I can just run something and then call sys exit. I can even okay, wait. I don't want to do this because I'm actually modifying the original one. Let me make a copy. Okay. But then I will have to run everything that happens. I will be with you in a second. This is again downloading. I need to run I don't need this one. Let me run this one and then the functions that I'm using. Basically, while I do this, I did try to get this sorted beforehand, but I messed up. Sorry about that. You can check this because this is what I'm going to explain in a second. The structure of this create label image. Basically, the main idea of this is just traverse all of the files in one folder. For those that are species masks, accumulate them. And that means make a file that's the same size as all of these files because everything is the same size. Everything is the same size as the mosaic. And first start with one file that's that size, the same size as the mosaic, and it's completely black. It contains only 0, and then iterate over all of the species masks. And for each species mask, change the proper pixels to the code of the species mask. That's it. But let me explain it a little bit in more detail once this thing finishes downloading again. How do I find out the name of the species, the code for the species from the file name? How do I This is okay. The error was expected. Okay, jumping that. And now I'm here. Okay, now I can happily modify. So, as I was doing before, I realized I was not modifying the correct one. I can just start by printing this file list thing. Okay, file list is a function, not file list. List dir is a function from the OS library, and that's why we have here the OS point, and then I could just print it. And as I was saying a second before, I can just do something like sys exit so that this thing ends here. I have not imported sys, so I get that yellow underline. So let's import it. And now if I run this, I get incomplete output here. I can just get rid of this. Okay. So let's see. So build it is not defined. Let me see what the problem is here. Let me just invalid escape sequence. Let me get rid of this one a second. For some reason, it's giving me problems at this moment. I will revisit it in a second. Okay, sorry, I see. So, okay. So, let me just run this a second. Okay, system exit. So, sorry, before, this is an interesting example. I was getting an annoying incomplete input syntax error, and it was not very helpful because it was telling me that it's somewhere in blah, 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 somewhere, okay? And I think it was not the fault of this thing which I assigned blame to incorrectly. What's Python was telling me with that error is that the input was incomplete. After messing it up and not finding it for a couple of minutes, I should have probably Googled it, or these days you can ask an LLM what that error is. But I finally realized that this was not important, and sometimes the error message is not helpful. It usually is, and I recommend that you read them, okay? But sometimes they are not. And I remembered to read all of it, the rest of the part. So this is saying that the input is incomplete, which it actually is, because here I have an if, and I have absolutely nothing, that no instruction inside of the if, and that's a problem for Python. So I just gave it a pass instruction to make it formally complete, okay? And then this is giving me some warning and so on, but this is still working. And then I can run it, and I get to the system exit because I put a system sys exit here. So now everything is running fine. Incomplete input means that I have some coding structure that's not right, and I did it. I left you here all of these indications that you have to fill, but because I had not filled anything, Python was complaining. Okay, so that was okay, my mistake. As we were doing, first of all, we just use this list dir thing, and we can print it, and we see a list of all of the files in the folder. Actually, the names of the file in the folder in string format. Okay, and I have all of the ones that I would expect. I'm calling it with S4 and I get these ones. If I call it with S6, I get different ones. Okay. Okay, so that's what I have in file list. So I'm not going to print it again. Now I'm going to continue. I have this base name, this call, which gives me the site name. This is going to be important because I'm going to be needing it to read some of the files. For example, if my site is 6, my ROI name is S6 roy.jpg. So I only need this part of the name of some of the files to get the name of the mosaic and also of the ROI, for example. The ROI is S6 roy.jpg, the mosaic is S6.jpg. Okay? So I want to extract that, and I have done this before for you with this line. Okay, I can print that one, site name, sorry, and I will get it there. Now I'm not printing the file list anymore, and I'm getting the site name only here. Okay, we already have all of that. The ROI name is, as you can guess, the site name plus ROI.jpg. Okay, as I saw before. Here we find this os.path.join. Okay, what would happen if I just called something like, I can read, how do I call it? Mosaic, for example. Yeah, read mosaic with a file name. Okay. So let's call this read mosaic function here easily. And let's just not worry too much about it. Let's just say S6 JPEG, which is one of the mosaics that I might want to read. Okay. And I'm going to call it my image and just read it. Okay. And then let's not call this. Let's just call this, okay? And here I get this non-type object is not subscriptable. So let's see what's going on. I'm getting some error here, okay? What is the error? It's in the readVM function, okay? Sorry, not in the readVM function, in the readMosaic function, which is the one that I'm calling now. It's telling me in this call to readMosaic, you have an error, and it's here, readval something something. When I'm trying to access the thing that I have read, I'm getting a message that says non-type object is not subscriptable. So I have gone into Mosaic, into the readMosaic function. I have read this with imread and so on. I have put it in a variable called readval. And that one, when I try to do something, this was to change BGR instead of RGB. If you remember when we saw it in unit 1, in the unit about DC, DL and CD, Deep Learning and Computer Vision basics, that when I try to do that, I get this error. Okay, non-type is not subscriptable. What is happening there? Again, I could just Google this. Let's see. If I do, for example, I get page from Stack Overflow, which is a very helpful page for this type of consultation. Sadly going out of fashion quickly because, again, of LLMs, but still worth a look, okay? And here I have some discussion. Python is a programming language with lots of people working on it, and some of them give very helpful suggestions, some of them not so much. But for example, this guy is telling the user, the exception the non-type object is not subscribable happens because the value of list is actually none. Okay? So what this means is that when I get to the end of my readMosaic function, here readval is none. So the return from this thing is none. I have not been able to read my image here. What happened? I have my image here, right? Oh, no, because my image is not here. It's inside of Datasara and site 6 and so on. Okay, so it's there. So I have not given the proper path to my function, and that's why it did not find the image. Okay. If I did something like data, let's see if I can write it properly, data Sara, and then S6, and then JPEG, then it takes a little while because the images are pretty big, but it does work. Okay, no error in this case. So my problem there was the path. And that's why when I'm inside of my label im function, come on, I need to be careful with the paths. In this case, I receive the root to a folder, and then I want to be always taking into account that I'm inside of that folder. So when I read something, the ROI, which is indeed site name plus ROI.jpg, I need to do what I just did. For example, S6 bar and then the name. Okay. I could just hear something like ROI name. Let me actually do it. I could do something like this is it would be site name plus this is a string, and then I have to add the bar, and then I should concatenate with that thing I was doing, site name plus ROI. And then I would not need the closing parenthesis. This would also work. Okay, this would be in this case S6, and this would be the bar, and S6, blah, 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 blah. This would work, okay? Because I'm already calling this with data folder with the data Sarah and the S6, okay? So in this case, oh, no, sorry, I'm messing it up. It should be folder, not site name, okay? Folder. Folder is already data Sarah plus S6. So here I would go get the data Sarah S6 and here bar s6.roy.jpg. Okay, so I could get this, but just adding, let's say, the bar in the middle and joining with the folder. The problem is that this will only work in Linux machines because they use this bar. Windows machines use the slash, so that will not work for them. So instead of just making the strings for the paths on my own, I'm using this join function from the path library, OS path library. So when I say join folder and site name plus Roy, what this guy is doing is adding a bar if I'm in a Linux computer, which will, by the way, always happen if you're in Colab, because they are all Linux computer, and it will add a slash if you're running it in your own Windows computer. Okay, so this OS path join thing is so that you don't have problems with that. Okay, so we're getting there. We have the site name, S6 in this case. We have the Roy name, datasara var S6 var S6 roy.jpg. And now we can read it. Okay, I have added, if Roy is known, complain. Okay, raise an exception. An exception is this kind of message that stops the execution and says, hey, there was a problem here. So if you're getting this Roy image not found problem, is that probably you're somehow not building this correctly, but this should work. Okay. Okay, so now I have read the ROI. Remember, the file that tells me where the important part of the image is. And that's a binary image with hopefully mostly 0 and 255 values. And as we saw before, maybe some in between. Okay, what do I want to do now? That's what I'm going to let you do for at least 15 minutes now. I want to do what I have here. So I'm going to first copy it in something called mask. This is where I will accumulate, where I will create my label image. I'm going to end up returning this mask. Actually, let me just put it at the end of the function. Here, at the end, I will return mask. Okay? Mask. This is my goal. I will build mask and return it there. What do I do? First, I copy Roy. So I have something that's the same size as the Roy, the same size as the mosaic, everything is the same size. And here I have copied all the values, the 2551 and the 0 ones. But then I use my images as NumPy vectors, as we saw last week, and everything that's bigger than 0, I set to 0. So now the values that were not 0 are now 0. The values that were 0 are still 0. So I have something of the right size that's all completely full of zeros. Okay, so now I have most of my work done. What do I do then? I have this loop that basically goes over all of my files, or all the files in that file list that I saw at the beginning, and then it calls the is species mask. If it's a species mask, it gets inside of in the if, and if not, it doesn't. Okay, so now I'm traversing only the files that contain species masks. And now I'm almost done with task number 4. Okay, and that's why I'm going to give you a few minutes to solve it. Now you need to use readVM to read the proper species mask. And you have to be careful with the name. This is going to be called something like S6 and then the name, okay? Actually, I will have it just here. You actually don't need to do anything too complicated. You have the file name here. You only have to join it with the folder. Okay, so OS path join folder and F, which you have here. Okay, if you do that, you can just call the readVM function and have the mask that you are processing at this moment. And then what do you have to do? Then you have to read the species mask, that's okay. Then you have to retrieve the species code. And that's a bit the difficult part and the part that I will tell you a little bit later. Okay? What do I mean by that? So, for example, if I have S6, S37, I have the name of the whole file there, but I need this part. So I need to read this part. Okay? Actually, not the S37. I'm mostly interested in the 37. Need to read this part of the string and turn it into an integer. And then what will I do? Once I have read the binary mask, read the species code, I just need to put all of the files that in mask, sorry, not in this mask. Let me do it again. All of the files in mask that, again, all of the pixels that in this mask that I have read here for the species are 0, which are the ones that contain information. In mask, I have to put the code of the species to them. Okay. That was not very helpful. Let's call this one SP mask. Okay, that's the one that I'm going to read. And then I'm going to end up doing something like I'm going to read SP mask and I'm going to get the code here. So I have to end up doing something like mask, the accumulation one, of those that in SP mask are 0, then that takes the value code. Okay. And that's the whole of task number 4. Okay. I'm going to give you 12 minutes, not 15, because I already did part of the explanation, to have a look at this, and then we'll have questions, some time to answer questions if you have them. Okay. So let me pause the explanation and the recording for a second, and you have some time to work on this. We are back with the explanation of the of how to solve this this task 4. Okay, so I'm not going to completely do it, but as I said, species mask is pretty easy to get. So you just need to read VM, and here you just need the name of the species file. F contains most of the name, but then you need to also add the folder. So something like OS path join folder, comma, F, and then this is the name, and this one is to close readVM. So this will contain species mask. If you want, you can add something like I had before. If SP mask is known, raise exception, species mask not found, that would be okay. This has to come from the name of the file, and this is a little bit more annoying. So for example, let me not read this because this is going to be a little bit long to run. So let me comment this one for a second, but the code is going to be a part of the file name. So for example, I could do file, which is a name from 0 to 2, and I would 0 to 4, let's say, and let's print that one. And I would get in every time instead of this S, instead of the full thing, I would only get, yeah. So this is the full thing, and here I get these initial 4 numbers, okay? So not numbers, characters, okay? So by using this kind of thing, I can actually get the species code pretty simply. Be careful. This one that I'm doing, starting from here, is probably not going to work great because this is site 6, but you also have site 11 and site 13. So you can solve that with 4 if you want, sorry, with an if you want, but that's a little bit annoying. I would recommend counting from behind. So this one is -1, -2, -3, -4. This guy is -5, and this guy is -6. And that's always going to be the name, the code that you are looking for, okay? I need to also cast it to integer because this is going to be string. And if I try to modify the values of my mask with a string, I will get an error. So that would also work. I get similar. Sorry, yeah, that's not right because I'm trying to transform an integer, something that has an S in it. If okay, if I do it like this, I'm still probably not getting it. Yeah, because this still has an S. If I did it between 1 and 2, then I would get the 6 and it would properly transform into an integer. Okay, this would be 6 all of the time. You do not want this to be 6. You want to end up transforming into integer with this int thing, but you want something else. Count from behind and do something, I don't know, let's see if this is between -8 and -4. What do I get? Then I get a bit more than I want, but this -4 is already correct. I think you can take it from here. This gives me the code, and then what I need to do is, as I said before, mask, my accumulation mask of all of the pixels that are, let's say, 0 in my mask, take the value code, okay? Minor thing, if I say just space mask equals 0 here, the annoying gray values that I saw before are going to trip me up. So actually, let's use something like for code for 0, something like anything that's smaller than 150 or some similar threshold more or less in between of the 0 and 255 value. And that will be okay. That will go and accumulate in this mask all of the values with the code that I have retrieved here in the proper parts of the file. Okay, once I have finished, I need to mask out everything out of the ROI. Okay, so again, mask of anything where the ROI is not 0 or is, in this case, bigger than 155, this would take the value 0. Okay. And that hopefully gives you a good view of what you have to complete in task 4 and send your questions. You can ask them here if you want now, because you have been thinking about this for a second now. And if not, send them by email as soon as possible. Okay? Any questions at this moment? Okay. So moving on, this is, I'm aware, a little bit of the stumbling block of this project, but from now on, everything is kind of downhill, okay? So for example, what's this data sanity check about? This is acknowledging that, as we saw in the images done by vectors notebook last time, most of the times, sorry, I'm lost here. Most of the times, human annotations have small errors, okay? Sarah did spend a lot of time very thoroughly working on this, but it's just unavoidable at some point you're going to make a line marking the boundary of one group of trees a little bit thicker than it should be, and do the same with a neighboring mass of trees, and that's going to end up creating annotations that are overlapping. Okay, actually, I probably can show you something really quickly. Let's see if I can. Yes, I think I can. 1 second. Yep. These are annotations from one of the medical imaging projects, okay, that we are working in. And we also have this kind of image annotations. I have them here in kind of a level image format. This is the brain of a fetus inside of the belly of his or her mom. And we have these annotations that mark some of the important anatomical structures in the brain of this fetus to see if all of the development is going correctly. And for example, this is the cerebellum, and this is something called the cisterna magna. And if you come here, you will see that the annotations are actually overlapping. Okay, see? So manual annotation, even done by experts, like in this case, expert radiologists, have this problem. In project number 2, task 5, we are going to detect those. And to detect those, we are going to follow a very, very similar type of strategy to what we just did. Okay. Basically, we are going to go over all of the files in one folder, create an accumulation mask. But in this accumulation mask, I'm not going to put the codes from every species like I was doing in task 4, but here I'm going to add 1 every time a pixel is present in one mask. Okay, so I'm going to do mostly the same, but I'm going to end up adding 1 to mask, to the accumulation mask, in every case. So that will give me +1 to the pixels that are annotated in this mask. When I do that again and again and again and do it for all of the pixels, for all of the masks, sorry, in the end, the pixels that have a 0 in them mean that they don't belong to any mask, and that's okay. The pixels that have a 1 in them mean that they only belong to one mask, and the ones that have a 2 or more in them mean that they are annotated twice. So they are conflicting pixels. Okay, so here you need to find those, visualize them using Matplotlib, and provide a list of the species that have the problem. And this is a little bit tricky. Okay, so think about it. If you're a beginner, maybe you can skip this part. This is the D2 part of it. Okay. In task number 6, we are going to be doing some census type calculation. So we are going to be counting the pixels for each species in each site, and then putting all of that in a pandas data frame that is very similar to what was done in the final part of the NumPy notebook, NumPy for mask image calculation notebook. Okay, so here we have the different masks, and here we have that's for detection of the annotation that can also have double annotation that can also help. And here we have something that does something that you can use for task number 5. Sorry, 6. Task number 6 for label image 5, double annotation 6, data frame. Okay. I'm going to finish today's class a little bit earlier because I have an exam in my next subject in about 20 minutes. But let me just say that I helpfully provided the answer for task 8. So this is going to be shorter. Beginners probably don't need to concern yourselves too much with anything past task number 6 or 7 if you're interested. 7 is not long. But for those of you a little bit more advanced, you have already pre-solved task number 8, a function to count the trees in one particular site. Okay, and this uses the connected component with the stats function. So do have a look at this one and understand properly how it works. Check, why am I doing this thing? Spoilers, we already saw the pixels that are neither black nor white. Here you have the connected components with the stats call, and how does that work? Check why I'm returning from 1 and not from 0 as I would usually be, okay? And that will give you the list of the coordinates of the points indicated in one of these treetops rows files. Remember this one that has a small black region. We see them as points, but they are actually small circles, okay? So this connected component with the stats is going to give me the coordinates of the center of each of these circle regions. So you will have them in this list. And then we want to create a pandas data frame of the trees per every class. Okay? So in that list, I will have all of the trees of all of the classes. I will have their coordinates. And if I take the label image that I built in task 4, then I can just check. I can just access, because I can very easily access, any pixel of any image. Okay, so I can print the pixels of my images, not this one, in the one from basics. Okay, I can just access an image as a list of lists, and I can print the value of any pixel. For example, yes, this one. Okay, here I'm accessing the one matrix, and here I'm in particular accessing one pixel of one matrix, a 0, 0 pixel of one image, as an access to a double list. Okay, so you can do the same in task 9 from this project by using the list of coordinates. Those are the x and the y. Remember, OpenCV order is not xy but yx, so check that. And then you can use that to know how many trees of each species you have. Actually, you use that access to know in the label image each of the tree tops, each of their center coordinates, what species it belongs to, and then you can use that to build the data frame. Okay, that's a task number 9, the data frame of trees per class. And then you have a couple more tasks about grouping them and making some pretty statistics. Okay, and I'm going to finish now, but even you have some more to just lean on the thing that this is working for different types of images, and these are some images provided by people at the geology department here in Yamagata University, photos from a volcano. Okay, so you can just run those and visualize them. Okay, sorry. Yeah, I didn't download the data. You need to download the data and then you can visualize it. Takes a while. Let me see if I can show it before I finish the class. I have some more difficult tasks. Yeah, see? Nice images of eruption impacts from, these holes, these impacts that are created from the eruption, from the projection of boulders, and the annotations that the people in the geology department did for us. And then we have some tasks trying to count them, to separate them, to use connected components and morphological operators. So if all of that initial part is easy for you and you want to get a little bit deeper into image processing, here is an opportunity. Okay, so we will finish the class here. As I said before, next week we'll have a Q&A session with, if there are no many questions, some further, let's say, deeper analysis of this. And I would recommend that you all try to solve task number 4, and that will give you 5 pretty easily as soon as possible, and submit your questions, your work to me as soon as possible. Then that would give you plenty of time to finish things next week and get high marks. Okay. Okay, thank you very much for listening, and we finish the session now.
Thank you.
Thank you.
Thank you.